The universe may not be fundamentally made of matter sitting inside space. It may be made of information, and space might be the way that information gets organized. I know how that sounds. When I say space might not be fundamental, I don't mean nothing is real. I mean something more precise. Space may be an emergent description, like temperature. And as we'll see, black holes will force this idea onto the table because they make where information goes a problem we can't ignore. Before we go any further, we need to keep our footing. This video is conceptual, no equations, and will separate what's well established from what's still being debated. Established, black holes behave like thermodynamic objects. They have temperature. They have entropy. And they are entropy scales in a very surprising way. Also established, quantum theory strongly suggests information is not supposed to simply vanish. More speculative, the idea that space-time itself emerges from deeper quantum rules, and exactly how that works in our universe. We'll talk about why physicists take it seriously, and where the uncertainty still lives. Here's the core question we're really asking. If you tried to write down the deepest description of the universe, its source code, would it be written in the language of space and time? Or would space and time show up later as a kind of high-level interface? Hold on to that, because we're going to circle back to it when we reach the strangest clue of all, why the information content of a region seems to care about surfaces more than interiors. Let's build intuition with something familiar, temperature. If you zoom in on a gas, there's no single molecule that contains the temperature. There are only particles moving, colliding, trading energy. Temperature is what you get when you stop tracking the details and start describing the collective behavior. And yet temperature is absolutely real. It's measurable. It predicts what happens. It decides whether water boils and whether steel softens. It's not fundamental, but it's not fake. So when physicists say space might be emergent, that's the kind of claim they mean. Not that space is imaginary, but that it might be a reliable summary, a compressed description of deeper microscopic degrees of freedom. Another analogy, a map. A map isn't the territory, but if it's a good map, it gets you where you need to go. And sometimes the map uses a coordinate system that isn't out there in nature. Latitude and longitude aren't painted on Earth. They're a way of organizing information about the planet's surface. Space and time might be like that. An organizing system that becomes natural and almost unavoidable at large scales, even if it isn't the deepest layer. One more analogy, because it helps later, a user interface. When you drag an icon on your phone, you're not physically moving electrons in the shape of that icon. You're interacting with an interface designed to hide complexity. The icon is real at the level you operate, but it's not the fundamental object. Now ask a dangerous question. What if distance and location are also part of an interface? What if underneath, reality is more like a network of relationships and geometry is how that network looks when it becomes smooth and stable? That sounds like philosophy. So we need physics, something that pushes us into this corner. And that's where black holes enter. Black holes aren't just exotic objects in space. They're stress tests for the laws of nature. Classically, a black hole is defined by an event horizon, a boundary you can cross inward, but you can't cross outward. Once you fall in, no signal escapes. If physics were only classical, that might be the end of the story. But quantum theory adds a rule that refuses to stay quiet. Information shouldn't simply be destroyed. To see the tension, imagine burning a book. When a book burns, the words don't survive in any practical way. But in principle, the information is still present in the exact microscopic state of the smoke, the heat, the air molecules, the ash just scrambled beyond any realistic recovery. Quantum theory is built around this idea of reversible evolution at the deepest level. If you knew the full microscopic state, the laws allow you, at least in principle, to run the system backward. Now imagine tossing the book into a black hole. If the black hole destroys information, then the fundamental rules of quantum theory would need to change. If quantum theory stays intact, then the information must be preserved somehow, even if it looks lost. This is the black hole information problem, debated for decades by physicists, including Stephen Hawking and Leonard Susskind. The details are subtle and still actively researched, but the pressure it creates is clear. Black holes force quantum mechanics and gravity to negotiate. And then comes the clue that makes everything weirder. Black holes have entropy. Entropy is, roughly speaking, a measure of hidden microscopic possibilities, the number of internal configurations that all look the same from the outside. If two objects have the same mass, charge, and spin, but many different internal microstates could produce that same outward appearance. Entropy counts that multiplicity. Here's the shock. The entropy of a black hole scales with the area of its event horizon, not the volume inside, the area of the boundary. This is one of those facts that sounds like a technical detail until you sit with it for a moment. If you think the amount of stuff you can store should scale with volume, black holes are telling you, no, the bookkeeping is done on the surface. It's like discovering that the maximum number of files a hard drive can hold depends not on the size of the box, but on the area of the casing. Or like finding a library where the number of possible books is limited, not by how many shelves are inside, but by the square footage of the walls. That is not how we expect physical systems to behave. So why does nature do this? One reason black holes are so important is that they seem to represent a limit. If you try to pack too much energy, too much information into a region of space, gravity responds. Push it far enough. And you don't just get a dense object, you get a horizon. A boundary forms, and the system becomes a black hole. In that sense, black holes are like nature's maximum compression objects. They tell us the upper bound on how much information can fit into a region before spacetime itself reacts, and the bound appears to care about area. Now we can introduce the next rung of the ladder, the holographic principle. The holographic principle is not the claim that the universe is literally a shimmering projection. It's a claim about description. It suggests that the complete physics of a volume of space might be expressible in terms of degrees of freedom living on its boundary, like a book that somehow contains its entire story on the cover. More carefully, the maximum information content of a region may be proportional to its boundary area, and a boundary theory might encode everything that happens inside. This is a radical reversal of the usual picture. We're used to thinking that the boundary is just the edge of the thing. Holography suggests the edge might be the place where the fundamental accounting happens. At this point, it's fair to ask, is this just a suggestive metaphor? Or is there a real example where the boundary description is genuinely complete? There is a famous example. It's not our universe exactly, and we have to say that clearly. But it's powerful because it shows that holography can be more than a poetic guess. Here's the intuition in plain language. There exists a kind of space-time with a particular curvature called anti-de Sitter space, where a theory of gravity in the bulk volume is mathematically equivalent to a quantum theory without gravity living on the boundary. Two different descriptions. One underlying reality. In one description, you talk about geometry, distances, and gravitational dynamics in the interior. In the other, you talk about quantum fields on the boundary, with no gravitational force in the same sense. Yet the two match, not approximately exactly, within the framework where the correspondence is defined. Now, an important limit, our universe, as far as we can measure, does not look like anti-de Sitter space. On the largest scales, our universe appears closer to a different geometry influenced by dark energy, and the details don't line up with the simplest ad setup. So ad-CF is not a finished theory of everything for our cosmos, but it is an existence proof. It proves something profound is possible, a world where gravity and space-time geometry are not fundamental ingredients, but emergent outcomes of a deeper quantum system. That alone changes what we should consider plausible. Think about what that means. If a boundary quantum theory can fully reproduce a bulk gravitational world, then space can behave like a derived concept. The bulk isn't necessarily the place where the true degrees of freedom live. The bulk can be a kind of effective picture that becomes natural when you zoom out. And that closes one of our earlier questions. Can holography be real physics instead of metaphor? In at least some controlled models, yes. So the next question becomes, if something like this can happen in certain universes, what is the general lesson? What is the universe really if space-time can emerge? Now we climb to the final rung, emergence. We usually imagine the universe as things located at positions in space, evolving through time. Space and time feel like the stage, matter feels like the actors. But black holes suggest the stage itself has an information capacity. And holography suggests the script might be written on boundaries. This invites a new organizing idea. Maybe the most fundamental description is not made of objects in space. Maybe it's made of relationships, correlations, quantum information constraints, and What we call space is the pattern that appears when those relationships arrange themselves in a stable way. One way to picture this is to imagine a network. Not a network embedded in space, a network that comes first, and from which the sense of space is derived. In such a picture, distance might reflect how connected two parts of the system are. If they share a lot of information, they behave as though they are close. If they share little, they behave as though they are far. This is not a single proven theory of our universe. It's a direction of research with multiple competing approaches. But it's an example of what space is emergent can mean in a concrete way. What about time? Here we need to be careful. The idea that space might be emergent has strong motivation from black holes and holography. The idea that time is emergent is more speculative and more controversial. Still, physicists explore the possibility that time, as we experience it, is tied to change, to how systems update, to how information is processed and coarse-grained. In some frameworks, time is not a fundamental clock ticking in the background, but a parameter that becomes meaningful when you describe the evolution of large, complex systems. If that's true, then asking what happened before time began may be like asking what's north of the North Pole. The question assumes a coordinate system that may not apply beyond a certain boundary. That does not answer everything. It doesn't remove mystery, but it might tell us why certain questions feel impossible. They may be asked in the wrong language. And matter? Even in standard physics, what we call particles are often best understood as excitations of underlying fields. In other areas of physics, we see emergence even more dramatically. Collective systems produce quasi-particles that behave like new entities, real enough to measure, manipulate, and use even though they don't exist as fundamental ingredients. So if space and time can be emergent, matter being emergent at some level wouldn't be unprecedented. Reality can have layers. A higher layer can be stable and lawful and absolutely real in practice, even if it's not the bottom layer. This is the key framing to keep us honest. Emergent does not mean imaginary. Emergent means effective, reliable, and not fundamental. So, what is the universe really? Here are three implications carefully labeled with what's solid and what's still open. But first, an established clue. With a radical taste, the universe seems to obey deep limits on information. Black holes suggest that if you try to store too much information in a region, you don't just get more density, you get a horizon, and the accounting becomes area-based. That hints that information is not just a human concept, it's part of the fabric of physical law. Second, a plausible but not fully settled idea. Space-time may be a high-level description of that information structure. In some models, geometry emerges from quantum relationships, and holography becomes the translation rule between two ways of describing the same system. Third, more speculative but potentially transformative. If space-time is emergent, then the Big Bang may be a boundary of our space-time description, not necessarily the first moment in an absolute sense. The Big Bang would remain real as a limit in our map of the universe. But the deeper territory might not be organized in moments the way our everyday time is. Notice what this does and doesn't claim. It doesn't say we're living in a simulation. It doesn't say physics is merely perception. It doesn't say the cosmos is a trick. It says something both modest and unsettling. The concepts that feel most basic to us, space and time, might be the output of deeper rules. Like temperature, like pressure, like the smooth surface of the ocean, emerging from countless invisible motions underneath. Black holes may be the reason we know to take that possibility seriously, because black holes sit exactly at the intersection where quantum information and space-time geometry collide. Let's step back and recap the ladder we climbed. Quantum physics strains classical intuition about how reality stores information. Black holes strain our ideas about what can be lost. Black hole entropy scales with area, not volume, suggesting a surface-based accounting. That leads to holography. The boundary can encode the bulk. That's TFT provides a working example in a special kind of universe, proving the concept is consistent. And together, these clues point toward emergence, space-time as a derived, effective layer. If that feels like the ground moved under your feet, that's a normal reaction. But here's the stabilizing thought. Even if space-time is emergent, it still matters. Emergent things can be the most important things in our lives. Weather is emergent, and it can reshape continents. Life is emergent, and it can write poetry. Temperature is emergent, and it can power civilizations. So the question, what is the universe really, may not have a single satisfying answer in one layer. The universe might be a stack of descriptions, each real in its domain, where the deepest layer is less like a place and more like a set of rules about information and relationships. And maybe that's the quiet, strange punchline. The universe is not only what it's made of, it's also what it can remember. If you want more calm, intuition-first documentaries on black holes, quantum reality, and the foundations of space-time, subscribe. And I'd love to ask you one question in the comments. If space and time are emergent, what do you think is more fundamental information, relationships, or something we haven't discovered yet?